OpenCV weekly webinar, and today we are going to talk with Nandakishore, who is one of the contestants in OpenCV AI Competition 2021. He's one of the finalists. We had about 1,400 applications, and out of those, we selected about 250 teams. And Nandakishore's team is one of the teams that got selected, and he's been making a lot of interesting videos showing his progress over time on how his Agri-bot has improved. The team name is Deepflow Tesseract. So welcome, Nandakishore.
Thank you, Satya Malik, for a wonderful introduction to our project and also to the team. And good morning, all, and good morning, Phil, and good morning, all the participants that are joining right now. So good morning, all.
Good morning.
So we'll go over the presentation in a little bit, and you will get a chance to introduce yourself in more detail. But I also want to welcome Phil, who manages the whole process of this webinar. He is the content manager at OpenCV. Welcome, Phil.
Hey, morning, everybody. As a reminder, we will be doing Q&A during the session here. Please use the Zoom Q&A functionality at any time to ask your question, and we'll do our best to answer as many as we can at the end. We'll also be doing a giveaway. We'd like to tell them what they'll win if they win the trivia question this week, Satya.
Yeah, so this competition is sponsored by Microsoft and Intel. And so as part of that, anybody who answers the question correctly, the first person who answers the question correctly, which will be asked at the end of this webinar, will receive 200 hours of free Azure credits for processing. You can train your neural network and do whatnot. So
thanks so much to our generous sponsors.
Yes, that's great. So let's get started. Nandakishore, would you like to put up the slides, and we'll go over the slides?
Sure. Yeah, great. So Agri-bot is actually an AI quadruped robot for agriculture sector, and so the history behind why we choose the Agri-bot, the story behind why we choose it is shown in the next section. We actually participated in the OpenCV Spatial AI 2020. We introduced the Agri-bot over there, so it's the second version of the Spatial AI competition, and we presented our first robot, which is actually a rover, to actually identify the pest that's on the agriculture crops, to identify and target the pest and spray pesticide on specifically on that crop. So the idea is very simple. You actually introduce a robotic rover which attached with actually attached with the OGD, which the depth camera that's provided by the OpenCV community. So you put the camera over there, and you put again a small arm over it, and I just spray the pesticide over it. So it's you can see a simple demo that I've actually presented on the finals of OpenCV Spatial AI Competition in the same way that our team has been entered into the finals and presented this idea, which is actually generally a simple robotic rover with an arm. It's the very rudimentary idea, which actually not so much perfected, and it has a lot of flaws happened during the making and during testing. So
well, it's the first cut, right? So the fact that it works right in the beginning, that's great. So this is the idea that was presented when you first applied for the competition, right? This is right. And what's doing is, just to clarify, it's basically finding the leaves or areas of the plant which are infected by pest, and spraying the pesticide only on that leaf, right? So that we do not have to treat the whole plant with pests, or just without thinking, we just don't spray pesticide all over the crop, right? Which is obviously a problem from a
ecologically it's a problem, and also just you're wasting pesticide. That stuff's not cheap.
Right.
Exactly. That's the problem that's we try to solve, and it's the first version. You can say it as a 0.5 version 0.5, and it's basically a rover. So that's the design part that I have shown here, which generally a simple proof of concept. What exactly that we are trying to achieve.
Right.
And moving to the next is what exactly that we are presenting here, moving from a rover to a quadruped. So
big difference. It looks so cool now.
Yeah, it's a huge difference. You can see a lot of things happening there. You have a robotic arm over there, and a tank, a small tank, and a small DC motor over there on the left side, and the Ogdi on the front side. So a
Right.
huge difference is happening here. So
And just to give people some background, you just graduated, right? You started this project where you were in the final year of your undergrad. So you've been doing this, learning yourself during the undergrad, your curriculum, right?
exactly.
Okay, that's great.
Okay, so the story is somewhat, it's like an adventure. How we actually, we have a team of 4 people that are actually working on the backend side, and actually I'm trying to connect with them and also getting the most of the information from them. And also we have a community called as a Spot Micro AI community over there to help us to solve some of the greatest problems that are facing this kind of quadruped robots. So we have a community or international community over there, and we have some people that are my colleagues currently working over this system. So it's
And
like an adventure. And
what was the
let's
motivation to go from a rover to a quadruped robot? Is it because in agricultural, environment, you cannot always have the smooth surface for the rover to go, so you need a quadruped? Is that the reason?
Exactly. That's the problem. That's the problem that we are trying to solve. So the problem is that is you as we taken the crop as cardamom plant. So cardamom is one of the most pesticide spraying plant that are that are in the market. So the problem with this terrain is that it's quite uneven. So we actually visited some of the field and in our area. So we see that the terrain is somewhat sophisticated. When you are moving, when you are integrating a rover system, you cannot actually uh, pull this to a further level. Even if you have a belt drive system, you cannot do it. So the terrain is quite uneven. So a quadruped robot uh, helps a lot. That's why we switched to a quadruped robot rather than a rover one.
Got it.
And as it progressed, we actually visited some of the farmers, and we found that they have some problem regarding the agrochemicals that are spraying, or they're making a lot of expenditure from their side. That's like a 70,000 per acre. So we choose this cardamom plant because if we can implement on this kind of highly sophisticated terrain, it's an easy task to implement on any agriculture field, like a vegetable field, or like a or like a like paddy field. Paddy field is quite sophisticated, so that's somewhat you need to switch to some other level of robots. So
Right.
if vegetable field is something that we can actually implement after we implementing on this small carbon plant. So see
And
the problem is, yeah.
just to give people, because it's written in rupees, just to give people an idea. So 70,000 rupees is essentially $1,000, and $1,000 is, I mean, it's difficult to imagine, right, when you have to convert it into the cost of living kind of thing. So $1,000 is, would we say that an engineer coming out of school, uh, $1,000 a month would be a good salary for them? Nandikishore, is that uh, Can we say that that's the right scale to think about
Yeah,
it?
exactly. Yeah, that's very right, because
Okay.
in countries like in India, people are living with the help of agriculture.
Yes.
So most of their money comes from these fields.
Right.
So if we can reduce to, let's say, 40,000, that's a lot. That's 30,000. That's with that we
Right.
are saying in Indian rupees. So that makes a lot. We can buy a mobile phone if you want. So it's completely online. People are going online. You can buy an Android phone.
Right.
So that's the spirit that we are trying to achieve.
Okay. That makes sense. Yeah.
Okay.
So what you're also saying is that the cost of the robot, because the cost of is let's say $1,000 per acre, you can with a lot of development cycles, you will be able to reduce the cost of the robot to something like maybe $1,000. Is that fair to say?
Exactly. That's we are planning, and
Okay.
actually, the first thing that we can do is take it as a subscription-based model,
Yep.
where people can actually use it as in a monthly payment basis, say
Right.
1,000 or 500 rupees for 20 to 25 rounds. So
Right.
that's an idea. That's a subscription-based model, because the most probably may cost some around 3,000 or 4,000 as of now, US dollars. So, after rigorous changes and mass manufacturing may reduce the cost to, say, 1,000 US dollars. So as a first step, we're gonna sell it as a subscription-based model. If it makes if it makes a better model after we tested the quadruped robot.
Got it. Okay.
We're seeing that business model a lot in agriculture and farming. Like, for example, Scythe Robotics is doing the same thing with their mower.
Yeah, Traptech is doing the same thing with strawberry farming. There are several. They are actually using the subscription model, and the reason is that people don't want to commit to big devices because they don't know how well it works. So they want to try it out first. But not only that, these companies also realize that it's much better use of resources or this equipment. Uh, the utilization is more if you actually do a subscription model. You can take it, every day it could be working, doing the work.
Yeah, that's the idea, so that people can actually afford it in
Yep.
countries like India, and countries like countries that depends on agri sector. So that's the spirit, that's the idea that we have. Yeah. Okay, I think let's move on to the next slide, right?
Yeah.
Okay, and right now we term this as a version 1.0, which actually a fully 3D printed version of Smart Micro. That's a fully open sourced quadruped robot, and you can find the STL files on Thingiverse. You just go on the Thingiverse website, you just search for the quadruped robot. You can actually find the exactly the same. The 3D printed designs or the STL files, and you can actually print it yourself. But we actually changed a lot on the stability, and also on the uh, on the making it as we test it to a lot of levels. Most of the times the leg breaks a lot, and it's like it's like a disaster when we are testing this. So we need to change it some sort of levels, so that it can be withstand some of the harsh environment that we are trying to test. So
Yep.
small changes happened during the progress. So right now you can actually take the print from the Thingiverse, and you can make it in your home. So it's not
That's
that
good.
much easy, that much complicated. You can actually do it.
How much time does it
Simple
take to
3D.
put this together? Let's say you have a 3D printer or you have access to the 3D printer. How much time does it take to put together? Let's say I don't know anything, right? I have, I'm a regular engineer. Um, for me to go and put this together and get it working, walking on its 4 feet, how much time would somebody spend on this? A day, or is it just a few hours?
For 3D printing for 24 hours, you may take 3 days to completely print this one. That's a 24 hours cycle. Or if you are printing for 12 hours and making it stop for another 12 hours, you can print it for 7 days if you want. So it depends on the on the printer, and also depend on the quality of your what is called as on the nozzles and everything. So it depends on the
and hopefully you don't have to redo any parts as well, because sometimes those prints will go bad on you.
Right. No, but once you have the parts, how much time does it take to actually assemble them together and have a working robot?
The first one is actually the motors. I'm using MT996R motors, which is actually hobby motors, and it's actually servo motors. You can actually buy it on eBay if you want. There's plenty of them on the website. And after taking that, you have to purchase the screws, nuts, and bolts. Yeah. And you have to have a Raspberry Pi, or you have to have a Jetson Nano. I use Jetson Nano because I have that in my garage right now. So yeah, just put it on there. And all the programmings and everything is actually available on the internet. You can search for Sport Micro from Mike. So he actually open sourced the source code for, you can actually implement on the Raspberry Pi. He actually had given plenty of information regarding that, right? Where you can actually build on your own. So it may take around 2 weeks to complete it. So from 3D printing to walking gates. So called as a gates. So right. it may takes around 14 days. That's the time.
Got it. And for people who are impatient, is there a way to actually buy the Spot robot instead of 3D printing it?
It's not there available in the market, but you can find the same one, which means more robust one called as Unitary A1 from it's from China. So it's not servo one. It's actually an BLDC one, or some DC motor one, where you can actually purchase from their website, Unitary website, and it's actually an industrial robot. So that's the cheapest one that's available in the market, and actually they are selling around in between 1,000 to 2,000 $. I don't know exactly what amount is that. You can actually buy one on the website, but for this one, I don't know if anyone is selling this 3D printer design. Actually, it's not there yet on the market. So that's the idea.
Okay. Yeah, that's exciting. Yeah.
So let's move on to that. So most probably plenty of webinars happened on the OFD. So I'm just giving why I'm used OFD on my Quadruped robot from a balance perspective and also from a vision perspective. So why I actually implemented is that it has the XYZ axis. That's the only thing that's when we are doing with balancing, and also along with in the arm, you have to design your arm, and based on this OFD that's provided by the community, or that's provided by the Lexonis community. So so the specification is shown here. Just you can actually see it. It has a 4 TOPS of visual processing, and it has modular structure, and you can actually implement on the arm that's shown before, or you can just put it on the front side or on the back side of your robot, and integrated with robotic operating system. That's you can actually make more intelligent. That's the Quadruped robot more intelligent. So that's why I actually implemented OPT with it. It's run really smooth on NVIDIA Jetson Nano, and it actually runs on Raspberry Pi Zero W, but it takes a lot of time to configure on that because I need to find the correct repo for it, and need to find the exact tree for it. I mean, need to get the exact version of Opti to work on that. So that's why I.
For people who are not familiar with OpenCV AI Kit with depth, basically it's a smart camera that has Intel's MediaTek chip inside it. So it can run any modern neural network on the device. And it also has a depth sensing capability. It has a stereo camera pair, and it's able to provide you with depth information. So it has 3 cameras, and 2 of them are used for depth. One of them is used for running neural inference. So the reason it's so fascinating is that the host processor, let's say you're connecting it to a Jetson or let's say a Raspberry Pi, the host is a processor is not being used at all when you're running a neural network. So your host becomes completely free to do business logic. And this is also a very powerful chip inside it, which has 4 TOPS of visual processing that you can do. So that's OAK-D.
Yep. And this is some of the tests that failed test maps, what are fail gates. So if you can see here, and also in here.
So can you explain a little bit, why do you call them failed gates, and what experiment are you doing in this video?
Okay.
So because most of the people here may not have a robotics background. So when you're doing this experiment, why do you call it a failed gate, and what experiment are you doing once you have printed the robot?
Okay, so the first one that we are doing is actually to align all the all the legs in a specific way. So say the servo motors works on the basis of the PWM signals, and you're providing the PWM signals or pulse width modulator signals on the motors. So each of the motors should be should rotate in a specific angle to make it stand. Say first thing that we have to do is make it stand, and the next one is actually make it move. So in here you can see the gates are actually the formulation and selection of sequence of coordinated leg and body motion. So it's nothing but a sequence of motion that makes the robot moves. So if you watch a dog or a cat moves, you can see so the legs are the diagonal legs are moves in the same synchronized way, and the opposite diagonal legs move in same synchronized way. Right. So that's the simple gates that we can say. So it actually fails because if you look at here, so if you just look at that's not moving in a synchronized way. The diagonals are actually not moving in a synchronized way. So just look at that. That's the problem that's happened over there. And the same way in here, I just put it on top of the camera. The camera is on the top, and the synchronization is not there. So it's
so the
that problem that's called as well.
The code and software that comes with the robot, does it not provide? Does it not work out of the box that you can actually get it out and ask it to move? You have to code that gate yourself?
No, it's actually simple. You have to calibrate each of the legs. Okay. But we call it as all the legs have to be calibrated into a certain angle, and which actually provided by the repo itself, where you can actually use your laptop or your PC keyboards to move all the left and right legs. We have 4 legs here, right, to its angles. So you have to note down the angles. Right. Note down on the YML file that's on the SRC file of the Catkin folder. So you have to put the YML file over there. So that's calibrated file. So what exactly happened is I actually worked on for almost 2 weeks on the same problem. It's almost 3 weeks, but the problem happened because I actually didn't look at the calibrated values. That's a pre-calibrated values provided by the repo.
Yeah.
So if you are actually building from scratch, say you have all the 3D printed models and you have all the motors, start with connecting everything together to the drivers and onto the Raspberry Pi, and start calibrating when you are joining everything together. So you don't do it after you put all things together, because the angle will change.
Right.
And the motors are actually 180-degree angle. So servo motors are 0 to 180-degree. If you put it in a wrong way, it won't work. So the important thing is you have to start from the when you're joining everything together, use the calibration angles and calibrate when you're joining everything. So most of the videos that are in YouTube say they are just joining everything together, and after joining they are calibrating, but that's not going to work. It may fail. So,
got it. But isn't it fascinating? This is an open source robot, and you probably have never met the person who created it, the original designs, but you're able to take that open source design, work on it yourself, and build on top of it. So you're almost, we are standing on the shoulder of giants in that sense. So that's the fascinating thing about open source.
Exactly. The problem is that he's implemented on Raspberry Pi 3 or Pi 4, but it's actually on Jetson Nano. Jetson Nano doesn't support the ROS kinetic.
Yeah.
It only supports the melodic. So you need to put a lot of library on the SRC file or the Catkin WP file folder. You have to change a lot. I got plenty of errors when you're actually building it. Yeah. And making it work on Jetson Nano is a tedious task when it is very easy to implement on Raspberry Pi, because the image file that are coming with Raspberry has already ROS installed. So you don't need to make any change. You just use the existing folder from the repo, and it's like taking out of the box everything and just implementing all that. But implementing on Jetson takes a lot of time.
Got it. Okay, let's move on.
Okay, let's stay. Okay, and see, now it's actually improved a lot, but not so perfect. So it actually moves, but it has some problem. It's not moving so fast. It's like moving on a stationary way. It's not that much fast right now, but it's improved a lot. You can see at 3 power bank that's powering this one, and this here actually the optimized gates. It's actually quite improved, and it actually runs a lot better than the previous one. That's the optimized one, and it actually more optimized than the previous one. So right now it's much better. So it's controlling from a keyboard, and the Jetson Nano is connected to a VNC. And that's I'm actually virtually controlling it. So it's connected to the same Wi-Fi. Actually, I can control it from my computer. So this is the optimized gates right now. So much better than the previous one. So this is actually what I've done. So I disassembled everything. So in the previous failed case, I have to disassemble every part to its scratch and to reassemble. And when you're reassembling, you have to calibrate.
Right.
So that made a lot of improvement.
Yeah.
It's like an optimization problem. You have to find the exact sweet spot to make it work.
Right.
And the next one is actually the most interesting one, where we actually put that on a grassy environment. That's the terrain that we will definitely implement. And in here, it's taken a lot of time when it is moving on this kind of terrain.
Yep.
And it's the most successful experiment that I have done so far on the walking gate. So right now you can see the camera is from a Raspberry Pi 0W. It's not from the Jetson Nano, I actually don't connected the Jetson Nano to it because it actually take a lot of power out of it. So when you're connecting to it, everything stops working. I need to connect it to an external power supply. So right now, actually connected with a Raspberry Pi Zero W. That's a small Raspberry Pi, and the visuals that are seen is actually from the Pi Zero W. And it's quite fascinating when it works on the field. It's so satisfying to see it on the field itself.
Yes, that's absolutely true. What about the, does the camera provide any feedback on the motion? Can it actually improve the motion of the robot, based on it has depth analysis, etc., right? So can it actually look at the terrain and say that, oh, this is the next motion, or this is how you should move next? Is that something that you do or plan to do in the future?
Yeah, that's the thing that I'm actually planning to do, and I'm actually trying to achieve that right now.
Okay.
The idea is actually you're getting the exact location values. That's the XYZ value. That is actually the distance between the object. That's the value that we want. And from these value, actually, we can either stop the bot. Say if the crop is around 2 meter distance or 1 meter distance from the board itself, you get the value 1 meter. So you say the bot, you say the command. So this command called is U. So the command can be entered, or it can be put in an if statement. Say that if the x-axis equal to x equal to, or if z is equal to 1, say you stop it. You just stop right there and spray the pesticide. So that's a simple task that's a hard-coded one that can be achieved in the coming days. I think that I'm currently working on that, how you can avoid the obstacle and also stop when something happens in front of it. So the problem with this kind of
terrain itself, what about the terrain itself? I mean, this is pretty uneven. So does the robot actually analyze the floor or the terrain to make smooth movements, or that's not necessary?
Or perhaps it's using Oak's built-in IMU.
Yes.
Yeah, that's the I think I actually put a video over there.
Okay.
Okay. Yeah. So this video actually on the IMU part, you see here, I actually use the IMU part to optimize on the leg motion. The better one is actually, it's a hard-coded program right now. The better one is actually PID controllers, where you can actually find the best solution out of it. So I'm actually trying to do the PID controller right now, but it actually works, but not so much responsive, but it actually works. So if you see here, it actually changes its orientation to adjust the situation. So that's the idea, and actually use the quaternion angles from the OGD. So this is right now the actual feedback that's getting from the camera, and it's integrated with the ROS. That's the core that powering the motion or the motion of the robot.
Yeah.
And this feedback has been fed to the bot.
So what you're looking at is OpenCV AI kit with depth. That's the video on the left. And it has an IMU, which is basically a sensor that gives you the orientation of the camera. And this on the right, you're looking at the output of the orientation as measured by the sensor. Is that correct, Kishore?
Yeah, exactly. That's the and it has the gyro and accelerometer value, and we are actually taking the gyro values from out of it. You get the values out of it, and you just mapping onto a visualization function that's provided, visualization library that's provided by the Python, and it's just showing it the gyro values. That's it.
Okay. So let's keep going. Your original slides. Yeah.
So the next one is actually the robotic arm part. There's a lot of challenges happen. There's engineering. It's an engineering problem. Either you have to put the camera on the board end, and or the right side, on the front side of the board. The actual solution you have to implement on both sides. You have to put one camera on the arm actually, and one camera on the board itself. And the idea is behind is actually you have to get the location of your arm and adjusting the board according to the robotic arm, and also you have to adjust the robotic arm according to the robotic quadruped robot position. So it's like
there are two OGDs on this bot. Is that right?
Yeah, but actually we are not integrated on the OGD on the arm yet, because it need to be adjusted, because the size of the OGD is quite much bigger, and the inertia, I mean the center of gravity, is actually preventing some of the problems happening in the. So the physics is actually the problem that's right now. So we are trying to achieve the both one, but right now it's on the right side. So you're just putting on the board.
Okay, so on the bot, almost like the eyes for the bot.
Exactly, that's right. Yep, I think let's move on to the next slide. And this one is actually have you see here, you have in here you have 3 motors. One is actually hidden here, so one motor is here. On the right side you can see the arm kind of thing, because for our case we didn't attach that one yet. And you have 4 motors, one on the attached on the top side of the board to rotate on 360 degree, and you have the XY motion the motors over there. So you have around 4 motors right now.
Yeah.
And let's move on to that. So basically the first the idea is actually, without the sprayer system, this is actually what we are trying to achieve. That's the experiment that we have done by detecting the crop or the say potted plant that's already on the provided model. That's the COCO model that's provided by the TensorFlow community. You make it as a blob model, a blob file for working on the OGD. So you get the location of the potted plant, and you set the commands over it, how much angle it should be rotated, and you put the arm end of the arm over there. So this is the first experiment that we have done without the sprayer system.
Right.
Okay,
so
in here,
this looks at all the potted plants, and once it locates a potted plant, it walks to the potted plant, and that neural inference, that determination that this is a potted plant, is being done on the OGD. Is that correct?
Exactly, that's right.
Okay, and then it walks to the potted plant, and does it walk autonomously? Does it have a or is it through the keyboard?
Right now it's through the keyboard. Right now it's completely manual right now, but the motion is autonomous. When the detection happens and the distance satisfies, the board arm should move towards it. So the quadruped motion is the gates are right now is actually manually controlled. You control it through keyboard.
Yeah.
And you can actually attach the PS4 controllers if you want. The repo actually provide that. You can actually connect the PS4 controllers if you want. So that's also an option.
Yeah.
And so right now you can see, as Satya explained, how it actually moves and sprays. All right. So it's actually integrating the sprayer system over it.
Always dangerous and interesting when you have electronics and water.
Exactly, that's the problem. That's the risk that I have taken. It's like months of work, but it can be destroyed in seconds if the water fall on the Jetson Nano. It's like it will be a disaster. You have to start everything from beginning. Right. So it's like taking a lot of risk when water is over there.
Yeah.
So in here, you can see how it actually sprayed. So it detects the plant. So right now it's actually using the Raspberry Pi 0W, and the OBDs are not attached to the Raspberry, not attached to the Jetson. It's actually attached to the Raspberry. Raspberry is the one that controls the robotic arm and the DC motor. That's a pump. That's the interesting part. We actually doesn't use the Jetson to do that. So that's the sprayer system for you.
Mm-hmm.
Okay, now let's move to the next slide. Okay, so this is the inverse kinematics. It's for a simple explanation, but for our case, we have a lot more motion happening. For a 2-point system, it's very interesting. You have your x value is called as a z. You see here for 4 point. It's like 467 meter. That's like say 46 centimeter, and that's the distance. That's the x-axis value, and you can take in the OGD value here, you can see here x or y here. You can take both of them if you want. That doesn't make much of difference. And using the simple trigonometry, you can actually calculate the angle. That's the angle that should be rotated. The servo should rotate that angle to reach that exact point.
Right.
So
is it
this idea is
when it detects the potted plant, is it detecting is it trying to make the roots at the center, and then it's trying to spray on not on the root, right? It has to spray on the leaf.
Yes,
Or the roots,
it actually sprays on the leaf itself.
Yeah.
It's actually you see in this case it's actually finding the center, and you in the experiment you can see it's pointing on the bottom side of it. I mean on the surface of the plant or the root.
Mm-hmm.
So you find the crop, I mean in the center, and finding other. For our case, we are trying to train the model on our data set, either on an SSD mobile net or an efficient net model, and convert it to the block file to make it happen. So in our case, it is on the leaves.
Okay. Great.
So for experiment, I've just shown it as on the surface.
Okay.
Okay. So it's already shown here. I have explained that part.
So you're using 3 parts of oak, right? First of all, the neural inference to detect where the plant is, and you're also using some depth estimates to focus the tooltip, right? Where to spray. You're using for your inverse kinematic stuff. You're using depth from OAK-D, and the final thing is that you're also using the IMU for stability on OAK-D. Is that fair to say?
Yes, exactly. That's the overall system right there. So
Okay.
So in here you can see you have your the DC motor that's powering the tank right now.
Mm-hmm.
And when it reaches to the destination, it sends the command. It's actually sends the command to the Raspberry Pi 0W to start the motor and spray for around 2 seconds, and stop it right there and retract the arm to the initial position.
Right.
So that's the simple logic that have been implemented.
Right. And in the future, the disease, the pest, the original idea where you're actually detecting whether there is some pest infection or not, right? Those
that's easy. That's an easy task. But as we analyze the situation and talk with the agriculture experts, saying that the pest identification is actually it's actually not that much efficient, because sometimes pests have happened on the bottom side of the plant or on the leaves, and it is so small that you cannot do it. The resolution is quite small, and the SSD mobile net cannot do, even if it has the pyramid network, the feature pyramid network. But even with that, you cannot identify the small pest. So the idea is actually just use the leaves to spray, to just identify the leaves and spray on the leaves, so that may kill the pest. So you exactly spray how much amount you want on the leaves itself. So targeting the pest is not a good option. So if one pest spread on to another plant, and it like a chain network, it travels everywhere. So it's not an ideal solution to target on the pest. So I think this is much better when it considering the efficiency of it.
Okay, sounds good.
Okay, shall we move on to the next slide?
Sure.
Okay, so this is the next version that we are planning to do, and the design is actually almost completed, and this one is actually using the BLDC motors, brushless DC motors, along with BLDC drivers called as O-drive, or any other kind of drives that are currently available in the market. And it actually, we are trying to either print it on carbon fiber or an aluminum chassis. So the second version is the most promising and most robust version, and the and can hold a much more capacity. I mean, the tank can be easily implemented over it. So the second version is currently that we are trying to build.
Got it. And keep in mind, on this webinar, we have, a very large range of solutions. On one end, we have people who are competing in OpenCV AI competition. And they spent about 3 to 4 months, right? So you guys actually spent about 3 to 4 months to build this thing, which is quite phenomenal, considering so many things can go wrong in hardware. 3 to 4 months of concentrated effort produced this robot. On the other end, we also see people who have spent years, right? Like the companies that we had, robotic companies we had on OpenCV webinar recently. They spent years in developing their robotic solution. So
yeah, I think Scythe had been what, 2-3 years they did work by then. Yeah.
So we have to keep things in perspective that this thing has been built in about 3 to 4 months, which is
under extreme circumstances with the global ongoing pandemic and the shipping catastrophes and all of this. Yeah,
that's right. And so you're planning to make this open source, right? The second version also.
The second version, we cannot do it because it's actually it goes to the industry. So the first version, we will open source it, and we are actually gathering every resources that we have right now to make it completely robust and also completely documented right now. So the version 1.0 will be open source, and version 2.0 is not yet open source, but you can find the exact design on the internet. If you search for a couple of times, you can actually find the design, and there are Discord community to help to design it. If you are so much passionate about it, you can actually design it if you want.
That's great.
And
so we'll put all these resources, Phil, you should work with Nandkishore and get all these links on the YouTube channel so that, people who are interested in this can get all
yeah, we'll definitely make sure that all those resources are in the video description for sure.
All right.
Yeah, everything is actually uploaded to YouTube right now. It's completely actually public right now. You can actually find it if you search specific keywords like agriculture, agri-robot, quadruped robot. If you search for something like that, you can actually find it. Say the filter to put the filter to 1 day, also today itself. You can actually find it right now. So that's it's actually right now. It's on the public. I'm not put it on an unlisted right now. You can actually find it's exact the same video.
Got it.
Cool.
Okay, this has actually happened right now. I mean, happened today itself, where some of our people actually visited on the cardamom plantation, and you can see the terrain that I have explained. It's so much sophisticated, where things gone pretty wrong when you're implementing the bot, and the physics is the problem that's right now that we are facing. the friction, the everything, the wind and the slope, everything. That's the toughest task to implement on this kind of terrain. So
Physics
this is
causes nothing but problems in my experience.
yes, exactly. So this has actually happened today. So some of our colleagues and some of our teammates, they are on the operation wing, that they visited to the farmer called PB Anish. He's actually an awarded Kerala government awarded farmer on a category called a best agriculture category. So he's actually an awarded farmer, and he has around 6 acres of farmland, ranging from cardamom plantation, nutmeg, pepper, coffee, dairy, hens, etc. So we got a lot of information out of it, how we can actually implement. And he's so excited about the Quadruped robot. He's saying that it's going to revolutionize his field. So he's a techie farmer, and he's also trying to achieve implement drones also. So that's future. So he's quite interested on our Agri-bot. So from a farmer perspective, there's a huge demand to use this robot on the field itself. So we have a testing environment right now ready to do it.
Yeah. That's great.
I think I finished my presentation right now. So
that's
so
great.
move on to
I
that.
mean, I'm excited to see the final. I mean, you still have a few days, and I know how these things go, right? The final push is always it produces miracles sometimes. So all the best for your submission, and we can open up for questions now.
Yeah, let's do trivia first here. So if you were joining us for the first time, the way this works is I'm going to ask a trivia question based on the slides from today's presentation. The first person to answer the trivia question correctly on the Zoom chat window on my screen will win a prize. Satya, would you like to tell them what they'll win?
Yeah, so you will win 200 hours of free processing time on Microsoft Azure. And this is brought to you by our sponsors, Microsoft and Intel.
Mm-hmm. Oh, and can you please unshare your screen?
Sure.
Thank you. So during the presentation, we learned a whole lot about this awesome quadrupedal agriculture robot. Of course, it's got an OAK-D hooked to the front of it, as you saw, but it's got a different platform built into the body. What host computing platform is built into the body of the Agri-bot?
Right now, it's actually
what you're saying. That was a question from the audience.
We got it. We got it. Hang on. Looks like
it's the audience. Okay.
Looks like Priyesh.
It.
Looks like Priyesh got it first. Jetson Nano.
Got it.
Take a screenshot here. Congratulations. We'll be in touch with you after the show to get your Azure credits. So yeah, let's do, we got quite a few questions from the audience here. We'll start with one about batteries. I saw that there were a few stacked on top of each other on a couple of those videos. What kind of power draw are you talking here? Like how long do you, can it actually run just on batteries currently, or do you have to, maybe disable certain parts to get it to be able to be out in the field?
Currently, the version 1.0 is actually it's a 3D printed model, and just implemented on PLA filaments. So after putting all the battery stack, that's why I got power banks. So it's a 10,000 mAh power bank, and the very next moment, all the legs broken. Boom. So the 3 legs have been broken, and I need to reprint it. And again, I put on that, knowing the risk. Again, one of the leg broken when it walks, and I had taken all the battery out, all the power banks out, and connected externally. So currently we have 3 power banks powering it. One is powering the Jetson Nano, one is powering the robotic arm, that's called as a Raspberry Pi is powering it. So you have to power the Raspberry Pi 0W. So that's the next one, and the third one is actually powering the OAK-D right now, and the fourth one that's we are trying to do is actually powering the DC motor. So that's the what we call as a the pump. That's pump that we are trying to do. So yes, we have right now it's actually using the 3 power banks.
Yeah, the power
So
is definitely one of the hardest problems in robotics, it seems like.
Nothing on the board.
Thanks for that. Somebody had an interesting question about scaling the bot. Do you have any plans for, say, what if you wanted to make one that's twice the size? Have you given any thought to scaling it up or down?
That's the version 2.0. That's the version 2.0 that I explained. That's the robust version. That's not using any servo motors. That's using the BLDC motors, using or drives and more rigid or robust chassis, and everything is either it should be in carbon fiber or it should be in aluminum. So that's the design that we are trying to do right now, and we are using the same software right now. Since BLDC drivers can be drive with PWM signals, so it's easy. You can just take the Jetson Nano, connect the encoder and encoder attached BLDC motors, and use the auto drive to drive it. So you can use the PWM signals to do it. So it's like mapping to the next model, so the next version. So it's going to be easy.
Cool. I had a couple of questions from folks about time as well. So how do you have any benchmark goals for like how many plants per hour you want the system to be able to service or check on? Were there like any hard goals, or were you just like, well, if we can make it walk, then we'll go from there?
Right now we don't have any pre-planned like it should be maintained, and say after planning and after spraying everything together, you have to take some rest right now. So here it has to be recharged, it has to be cleaned, and it has to be if something happens to it, it has to be changed. So right now it's completely in a prototype version. Right now it's like prototyping and optimizing it to work on the field that we are trying to do. And if it works, we are planning to make it more of a practical way of doing it. So you have to check all these kind of things. So that's the next part.
Yeah,
so
that's
right
always true.
Prototype.
That's always true in the beginning, right? I mean, if you look at the first prototype of Oak, it was literally a basket like this size, and now it's tiny, right?
Yeah, with like zip ties, and I remember that prototype.
Right.
Yes. So that also takes the information from your customers, where people have a lot of suggestions how you can improve the, say, if you have the OpD, you have I think I have the first version of OpD. First version is actually not the first version. I don't remember the version name. The 3-ribbon one. I don't know the name.
Right.
Exactly. The RGB camera and
it's a 1097 maybe.
Yeah. That kind of a disaster happened. So I cannot make it. I mean, the 3D printer is actually I actually bought it around 2-3 months before. I mean, it's like January. I just purchased January, February 2021. And in that time, I didn't have any 3D printer, so I cannot 3D print any frame or
anything to like protect the hardware. In other words,
and also you have to calibrate it on your own. So you have to put everything together. You have to make it 2.5 meter, 2.5 centimeter, and you have to calibrate using your the check maker, just
right.
I hadn't thought of that. That makes sense. That it's a more complicated situation than it might appear to be. Yeah.
Yes.
A couple of people have asked again this week, will this video be uploaded anywhere? Yes, it will be uploaded to our YouTube channel. You'll be able to see this as well as every other episode. This is, in fact, I think, Satya, this is episode 20.
Wow. I didn't even realize.
Can you believe it?
Yeah, so it's on our YouTube channel. If you go to YouTube, search for OpenCV.ai, you will get to our channel, and there is a playlist called OpenCV Weekly Webinar, and that's how you can find all the. You
can also just search OpenCV Weekly Webinar on YouTube, and it'll pull up on there as well. I think we're about up at time. Satya, would you like to take us home?
Yeah, thank you so much, Phil. Thank you so much, Nandkishore, for demonstrating what you have built during OpenCV AI competition. And I wish you all the best for your final submission. And all our audience, thank you so much for your support and for being here. We'll see you next week.
Yep. Thanks for joining us again, everybody. See you next week, Thursday.
Thank you all.
9 a.m.
Thank you, Sophia. Thank you. Cheers.
Thank you. Thanks so much for watching this episode of the webinar. Please hit that like button, subscribe, and don't forget to tap the little bell icon to be notified when new episodes drop. This week's episode was brought to you by Microsoft Azure and Intel, sponsors of the world's largest spatial AI competition, OpenCV AI Competition 2021. If you'd like to be in the audience next week, subscribe to the OpenCV newsletter.